All right, let's start. Okay, so yeah, we are learning about how to solve linear systems, which means we have to know what the values of an x1, x2, x3, and so on from these set of equations that we are given. Okay, so the linear system again is this set of an equation, and our task is to solve what the value of these variables are. Okay, and then last time we learned how we can convert this set of equations into a matrix, right? So we just simply bring those coefficients or the weights associated with each variable x1, x2, and x3, and also some constant on the right hand side. So this first row or horizontal vector is corresponding to one equation, right? And then the vertical vector in this matrix is corresponding to a particular variable. So this first one is all corresponding to x1, right? But from equation 1, equation 2, and equation 3, and x2 and x3, and this one is coming from these constants, right? Okay, and then now let's recall how we solved these set of equations from our high school or middle school. So the way to solve this equation is to basically eliminate one variable at a time from these equations. So first, let's pick up this equation, and yeah. Let's pick up these two equations, the first one and the third one, and then let's try to eliminate the variable x1 from the third equation. So in these two equations, we see all the variables x1, 2, and 3 in both equations. So we want to remove one of them at least from one equation. So how we do it is we simply multiply the first equation by 4, and the resulting equation is this, and then we add them up to, add them up to the third equation. Okay, and then we know these x1 is now canceling out with each other, and thus the resulting equation will only involve x2 and x3, right? So that way we created or generated another equation that only involves the two variables, not 3, right? Okay, and then let's call this one as 3 prime or 3 dash, which means our new equation 4, this equation 3. Okay, so instead of using this, we now use this. Okay, we know this kind of operation doesn't change our solution, right? It doesn't affect what the value of these x1, 2, and 3 is, right? So after replacing or after using the new third equation, we now have these set of equations. So this one is 1, 2, and it's 3 prime, right? And then from the matrix matrix representation, we can represent them in this manner, right? Then following this matrix notation, we can see that this kind of operation of multiplying the first equation by 4 and then adding them up to equation 3 can be also thought of as follows. So we just multiply the horizontal vector by 4 and then add it to the third row or third horizontal vector, right? Because that was our third equation. It's quite easy, right? So, so this is a linear algebra course, which basically is all about the matrix or this kind of set of numbers in this rectangular form. So we now learn gradually how we can utilize or how we manipulate purely using this matrix notation instead of these set of equations, right? So we now see the connections between this and this, right? So manipulating each row in this matrix will correspond to changing one equation into another form. Okay, and then the next step that we can do is, let's see, we now multiply equation 2 by 1/2, which means in this equation, this guy and this guy involves only two variables, x2 and 3. But for the first one, or this second equation, let's just make this coefficient as 1. Okay, and then we can simply multiply this second equation by 1/2. Then we have this equation, right? So we now have, so this is first one, and we now have a new second equation, right? So far so good, right? And then from the matrix point of view, we just simply scale or multiply the second row, right? Still horizontal vector corresponding to this second equation by 1/2, right? So that way we obtain this. Okay, and then the third step that we can do in order to solve. So what we are doing currently is to obtain x1 through the values of an x1, 2, and x3. Okay. So between these two equations, we can now remove x2, okay, from the third equation. So in order to do that, we just multiply the second equation by 3 and then add it to the third column. And then they are cancelled out. And then the remaining variable is only x3 with some constant on the right hand side, right? Okay, then this resulting equation will now be our new third equation. Okay, and then we can replace it. We can replace this old third equation with the new third equation, which will change the third one into 0, 0, and 1, and 3. Right. So this one will be our new third column. New third row or horizontal vector. Okay, so in this matrix form, we now have this kind of form. And then from this matrix, when looking at the shape of this matrix, we can see that it's kind of triangular form, or it has some kind of a staircase. So we start from here, and then we step up into higher staircase or higher floor, and then so you can think of it as a kind of reverse gravity. So the person is standing like in the reverse direction, okay, from this stair. And then we stepped up, and then we go a little bit to the right, and then we step another step up, okay, and then we also go to the right, and then until we meet the wall. Yeah, we go to one step higher. So that way we can see this kind of a triangular matrix where the upper right part is is filled with the non-zero values, but the left lower part is all filled by zeros. Okay, so we see 0, 0, 0 here. Okay, so this staircase is really meaningful, and for at least maybe around 2 weeks from now on, you guys will solve this kind of problem, and you guys will have to basically change some matrix or some equations into this triangular form. Okay, but how we can do it is really easy. We can just cancel out or eliminate or remove some variables like x1 in the third equation and x2 also in the third equation, and then also x1 in the second equation, and so on, right? Okay, and then we know this is corresponding to this, right? And then from here, it's much easier form to solve. So looking at the third equation, we simply know x3 is 3, right? And then what about x2? What about x2? What is the value of an x2? Right? Yeah, it's a 16. And how did we obtain that value? We just simply plugged this x3 into here, right? And then from here, we now have a x2 value. And then what about the last variable x1? We can also plug this guy in to here, and then x2 into here, right? So it's like, so we make this kind of triangular form, and then we just simply plug the last value or the value in the really last equation into higher equations. Okay, and then let's also try to represent them. Represent this process in also this kind of matrix form. So plugging this x3 value into the second equation, we can also represent it as this form. So this is our third equation, but it was transformed twice, and then this is just simply multiplication with the third equation by 4, and then add it to the second column, right? And then we can remove this x3, and then now we only have x2, which has the value of 16, right? And then this process can be viewed as this. So we originally had 0 and 1 minus 4 and 4 as the second row, right? And then this second row was replaced by the new equation of this, right? By just multiplying this guy times 3, this guy times 4, and then add it to the second column, okay? So we changed it, or we replaced the lower parts of an equation. But now, once we created this triangular form, and then we now replace the higher equations, or the equations in the above. And then what we did is here we created this 0, right? Because we eliminated this x3. And then we can do also the same thing by replacing the first equation by just canceling out this variable of an x3. And this is actually the same as plugging this x3 value that we obtained from the last equation into the first equation. Okay? So in this first equation, we can simply add this guy times minus 1, and then add it to the first row, or first equation. And then we can remove this x3. And that is the same as plugging this x3 value as 3 into the first equation. So that way, in this matrix representation, we introduced, or we changed this corresponding weight value or coefficient value for this x3 as this 0. Okay, so from this rectangular, once we identified this x3 value, or after we changed or made the value of this guy as 1, and then we look in the above, just right above the equations, and then change all these values by 0. Okay, so that is what we are doing. Okay, so using this, we created 0 here and 0 here. And then originally we had this kind of a staircase. You guys remember that, right? And then we now, once we finish it, creating zeros here, and then we now go back to the staircase by just going down. Okay, again, it's like a reversed gravity. So after stepping down, and then we look at this guy, and then also we look in the above, and then we now see this minus 2, right? And then it's time to remove this value as a 0. Okay. Okay, then after doing this in this matrix representation, let's change them into a equation form. Okay, and then the first one is x3 equals 3, and then from the second equation we created 0 here, and so it means we have x2 as 16, or equal to 16, and from the first equation we see 0 two zeros here, and we only see x1s. And so x1 is equal to 29. Right? So yeah, that's how we can solve this set of equations using this kind of matrix representation. So what we did was we basically replaced one row by a new row by adding or subtracting some multiples of the other rows, right? So here, yeah, we multiply the third row by 4 and then add it to the third column, right? And then used the new third column, third row or third equation, right? And so that's how we change it or created these new third row or horizontal vector in this matrix. Okay, so this is a key operation. And then another simpler operation that we did here is just scaling a particular row. So we simply maybe multiply a certain equation by 1/2 or 2 or 3 and so on. Okay, this value is depending on our equations coefficients, but in general this is a second type of an operation that we did here. So we just pick up one equation and then just multiply them by a certain number. Okay. And then there is a third type of an operation that you have to remember. So we learned two different types of an operation. One is a replacement, and then the other is just a scaling of a particular equation. And then the third operation is just simply switching the order between the equations. So that particular operation was not involved here, it was not included here, but it's also the simple one. Oops. Yeah, so for some reason we want to switch between these two equations. So so this one is becoming our first equation, and then this one is our second equation. So the order between these equations doesn't matter, right? So it doesn't affect the value of an x1 and x2 and x3, right? And so we can freely change whatever equations in terms of their orders, right? So that is interchanging between two equations, I mean the orders of an equation, and that is corresponding to, for example, changing this horizontal row in this matrix. Okay? So this is the third operation. And still, this doesn't affect the solution values for x1, x2, and x3. So these are the three operations that you guys can do. Okay, and then we can just verify if our solution was correct just by plugging these solutions into the original equations and see if they are all true. Okay, so we now have this elementary row operation. So again, we learned three different types of an operation, and they were all done. In different rows, right? So this operation is done with respect to rows, and then the first operation is replacement, and then second one is the scaling that we learned or that we did, and then the last one was this interchange. So we pick up just the two equations and change their orders. So these three are called this elementary row operation. Okay. And these three operation again doesn't change your solution, and the reason for doing a particular row operation among these three is to be able to solve those values of our variables x1, x2, and x3. Okay. So from that sense, we didn't change the solution set. Okay, so we didn't affect the actual the true value of x1, x2, and x3, right? So that way, this kind of new set of equations. So this can be viewed as another set of equation, or simply we call that as a linear system, right? And then the solution for this system is still the same as the original set of equations that we were initially given, right? And in these cases, when we have two set of equations or two linear systems have exactly same set of solution, and then in that case, what was called? Do you guys remember? Yeah, so if the two linear systems have the exact same solution set, then we call them equivalent. Okay? Now, in this new slide, we see the new term of row equivalent. Right? It's almost the same, but the first one was about the two linear system, which doesn't necessarily involve any matrix notations. But in this case, we think about the two matrices from the two different set of equations. Okay, and then purely from these elementary row operations, when we can change one matrix into another matrix by only using these three possible row operations. Okay, again, we were able to change one matrix into another matrix by using some of these operations, but not any other kind of operations. And in that case, those two matrices are called row equivalent. Okay, which means rows are somehow equivalent. So the first row is equivalent to the second row, and then the second, the first row is equivalent to the first row in the second system, and then the second row is equivalent to the second row of the system. Okay, but this row equivalent is actually the same as the equivalence between the two linear systems, because when thinking about the corresponding linear systems, they have exact same solution set, right? And then also, when thinking about this matrix version, we know that these three operations doesn't change or affect our solution set, right? And if we can change one matrix into another using these operations, we call them as row equivalent, right? So, row equivalent, two of the row equivalent matrices will have the two linear systems that are equivalent. Okay? Okay, then last time we learned about the three possible cases in terms of the number of solutions from our set of equations. So we can either have a solution or not. So again, given a some linear system or set of equations, we may be able to find some solutions, but we may not be able to find any solutions at all, right? So in just a simple in this case, we know that this guy has a solution, but what about this? 2x plus y becomes 3, and 4x plus 2y equals 5. And in that case, we know this case is corresponding to this kind of a parallel case, right? Which doesn't intersect or it doesn't meet in any point, right? we know the intersection and their corresponding point is corresponding to our solution set, right? Or our one of the solution. But when they are parallel, then and then we know that they don't have any solution at all. They have basically no solution. So we can think about these two cases: no solution or at least one solution. Okay, solution, we have solution or we have no solution. But in the case of having some solution, we can have just one solution or infinitely many solutions, right? So when thinking about the two straight lines, they can either meet at one single point or they can be just coincide with each other. In that case, we can see many possible solutions. But it's not possible to have maybe 2 or 3 intersection points, right? Because it's just a straight line, so they cannot bend, right? Okay, and then when the linear system has a solution, then we learned that in that case the system is called consistent, which means at least one solution. And then if the system is inconsistent, and then it means it is the same as we don't have any solution at all. Okay, and then if so it's not that important, but this existence, and so it means whether we have a solution or not, or the solution exists or not. And then if the solution exists, and then whether the solution is unique or not is kind of an issue that we have to find given a particular linear system. Okay, and then let's try to find out if whether a particular linear system has a solution or not, or if they have a solution, whether they have one solution or infinitely many solutions. And then the way to do it is just simply solving this equation by just using the tricks that we just learned, by using like 3 different row operations, right? And so we change them into this matrix form, and then now we can only manipulate this matrix without involving any of the original equation form. Okay, so we can now throw this away, and then we can just maintain this matrix form, right? And then so here the first operation that we can do is row interchange that we didn't do in the previous example. So the reason is because we have to first form the staircase form, right? But here the stair is like this because we already see 0 in the first place. And then now we want to step up because we hit the wall of non-zero value. But now we have to go to left in order to, because these are also walls, right? But in this staircase, we can either go up or go down actually, and then go to right, not to left. Okay, so that's our rule of creating this staircase. Okay, so in this case, we have to make them or change them into 0 so that we can have at least avoid going to the left, right? So in that case, we have no way to remove this value by using the first equation. So one operation that we can do in order to solve this situation is to simply switching them up. I mean switching the 2 rows, right? That we called this interchange. Okay. So let's simply change the orders of the first and the second equation. It's easy, right? And then it's equivalent to changing these 2 rows. And now we have this matrix, right? So we change it or interchange it, these two rows. And then now we formed some staircase. But here, yeah, we hit the wall and then we go up. And then we have to go left because of this, right? So it violates our rule. And so let's try to remove this value. How? We can just multiply this guy by how much? Eh? Huh? Half. Okay? So in that case, you want to change this equation as, so the student suggested multiplying this by half or scaling them by half, which will give the new first row of 1 and minus 3 over 2 and 1 and 1/2, right? So this can give our first row, right? So yeah, you can either do this operation, okay, and then another possible operation can be just to simply directly apply the row replacement. So which means we just multiply this guy by minus 5 over 2. And where does this value come from? It came from this value of 2 and 5. And then after multiplying this equation by minus 5 over 2 and then add them up to the third row, and then we can remove this value, right? But you can first create this row and then multiply it by minus 5 and then add the third row. I mean, it's the same, right? So it's up to your preference. So you can either do scaling first and then do the row replacement, or you can just directly do row replacement. But still, in this case, what we did is the same. We created the zeros here. So we want to make this value as 0, right? Because we are creating the staircase. And so we created 0 here, and then now we have some staircase like this, right? Right? But this staircase, yeah, we are not satisfied with this staircase because our leg is really short, so we cannot go up with the two floors high. So we can only go up by just one floor. Okay, so which means after so once we stepping up with the one stair, which means so we stepped up, but now we cannot go higher, right? And then it means by using this value, we have to create this value as 0. So if this guy becomes 0, and then the staircase will be flat at this moment, right? So it means by using this variable, we are removing this value as changing it to 0. Okay, and then how we do it is we simply multiply this guy minus 1/2 and then add them to the third row, right? Okay, and then we now made this staircase as flat. So yeah, we are now satisfied up to this point. And then we go to right until we hit the wall. And then this guy happened to be just 0 as well. So it means we try to make this value as 0, but together this value happened to be also another 0. So that is possible. In that case, staircase goes to the right until we hit the wall. And this is our staircase that we finally created. So it satisfies all the rules, right? So we go to, we go down and then or go to right. And also when going down, we only step down just one floor, right? And it doesn't matter whether we go to right with the longer distances. So yeah, it doesn't matter to us. Yeah, so this is our staircase kind of a shape, or just kind of upper triangular form of our equations or matrices, right? And then let's think about its equation version. So it will correspond to some set of linear equations. And then let's focus on the last one. And the last one is 0 times x1 and 0 times x2 and 0 times x3 equals 5 over 2, right? So suddenly we obtained the last equation as like a 0 equals 5 over 2, right? So this is clearly not possible, so it's impossible, right? And so let's suppose we are given this equation originally, okay? And then someone says 0 should be the same as or equal to 5 over 2. So it's already impossible, right? So we can simply say that, okay, so yeah, there is no solution, right? So we are happy at that moment. We don't need to try to solve x1 or x2 and so on, because it's already, we already know that there is no cases where we can satisfy all these equations because of this last already impossible equation, right? Okay, so this kind of case is corresponding to this inconsistent case of linear systems. Again, the meaning of an inconsistence is that we don't have any solution at all, right? And then, let's see. And then this kind of, this set of equations is actually the case that we are already familiar with. So we know, as I mentioned in the previous slide, this guy, which are like having the parallel line. So in that case, we know there exists no solution. So we know there is no solution in that case, which are having the parallel lines, but their y-intercept or these values are a little bit different, right? So these were having all the ratio of 2, right? So 4 is 2 times 2 and 2 is 2 times 1. So the ratio was all the same as 2, but the ratio between these are constant. It's not 2, right? So in that case, this is corresponding to the case where we have a parallel line, right? So this is exactly the only case where we have no solution, even when we have many variables. So in this case, we can think about only the lines, right? But it could be like in three-dimensional kind of plane when thinking about 3 variables. So what if we have x1, x2, and x3, and then maybe have a set of 3 equations. So we are given 3 equations, but we now have 3 variables. And in that case, we can think of about this inconsistent case as exactly the same as this one. So somehow in the 3-dimensional case, one equation is representing some plane, some straight plane. So for example, x1, 2x2, and 3. Let's use a different. Minus 3x3 equals 5. can you imagine what kind of a plane it is? I believe many students already learned about this hyperplane and its equation from high school, but yeah, let's review briefly. So x1, 2x2 minus 3x1, 3x3 equals, for example, 6. In that case, how can we draw the hyperplane? One simple way is thinking about the intercept. What is intercept in Korean? Or 절편. 절편이란 말 들어봤죠? y절편, x절편. 절편이 이제 자르다, 절단내다 뭐 이런 거 있잖아요. 우리 관계를 절단낼 거다 뭐 이런 거. 예. 그래서 어떤 이 축을 싹 절단내는. So intercept means we are crossing a particular axis at a particular value. Okay, so that is the meaning of the intercept. And then so this one is x1, x2, and x3 as our axis. And then what is the x1 intercept? It is 6, right? And then x2 intercept is 3. And then x3 intercept for x3 axis is minus 2, right? So it's like okay. I'm not very good at drawing. And that's why I'm majoring in this engineering. But yeah, it's like this kind of plane, right? Just a straight plane. And then let me give you another equation for plane, and that is 2x1 and 4x2 and minus 6x3 equals 10. Okay. Okay, so in that case, you guys know this plane is parallel with the first plane, right? Because we know, let me use different color, 1, 2, 3, and 2, 4, minus 6, having all the same ratio. But this guy doesn't have the same ratio, right? And then in this parallel case, we know that there is no solution, right? So this is a simple extension to the three-dimensional case. But what if we have 4 dimensions, where we have 4 different variables, or 5, or 100 variables, or hundreds of thousands of variables? We can still think about this parallel plane. But now, this kind of plane, I mean, if you think about the plane like this, in this 3-dimensional case, in much more higher dimensional space, like in a 4-dimensional case, what should be the shape of the plane in the 4-dimensional case? But still, this 4-dimensional plane will be just corresponding to one single equation. So yeah, let me just give you one equation, x1, 2x2 minus 3x3, and maybe 2x4 equals 5. So yeah, although this looks a little bit messy, but it's just simply one equation that involves 4 different variables, right? But in the geometric sense, I mean, when trying to understand this equation as a some kind of plane in 4-dimensional case, although we cannot imagine the 4-dimensional space, but this one is corresponding to some plane. But that plane, if we think about the 3-dimensional case, our entire space is a 3-dimensional, but our plane is 2-dimensional, right? So one less dimension in order to define our plane, right? But in the case of 4 dimensions as our entire space, and then the plane is actually 3 dimensions. Okay, so in that case, this plane is called hyperplane. It's like, in Korean, what would that be? Hyperplane. 뭘까요? 하이퍼플레인. 하이퍼. 네?
초월.
네, 초평면이라고 해요. 초평면. 초시아 여인 같은 거 알아요? 초시아 여인? 몰라요? 드래곤볼 안 봤어요? 그럼 명작을 안 보다니. 네. Okay, so yeah, this is called a hyperplane. And then, yeah, we cannot imagine this what the shape of this hyperplane is in this four-dimensional case, but we can still think about one characteristic. So if you remember this equation for plane in the three-dimensional case, we learned about the normal vector. Normal vector. What is that in Korean? 네? 곱선 vector. So normal, yeah, in a sense in the mathematical world, normal is like a perpendicular, okay, having a 90-degree angle. So that is a normal vector. And then we know the normal vector for this equation is something like 1, 2, and minus 3, right? So this is a normal vector, which means this vector is perpendicular. It's like this. So when given this plane, given by this equation, and then this normal vector, we just extracted out each of the coefficients, right? And then this vector is perpendicular to any vector in our plane, which means we simply pick up this vector, included in or contained in this this plane, and then originally this two vector is not meeting, or they are not intersecting with each other, but we have no problem of like shifting or moving one line to have one single point, intersection point, and then now we can think about the angle of it, right? And then this kind of angle is always 90 degrees given whatever vector we choose contained in this plane. Okay, so this is our normal vector. And then this normal vector, the notion of this normal vector is still the same in the case of a four-dimensional case. So in the four-dimensional case, it's 1, 2, minus 3, and 2. So this one is our four-dimensional normal vector that is perpendicular to any vector in this hyperplane. Okay. Okay, so back to the slides. Yeah, okay, let's go back to this original situation where we have a parallel plane. Okay, in that case, let's try to, suppose we had like 1, 2, 3, and 6, and then 2, 4, 6, and 10. And somehow this guy was the two rows in our linear system matrix. Okay, and then so suppose this guy was the first row, and then so we now have to have a staircase like this, and so we are removing this guy, right, by just multiplying the first equation by 2, and then no, minus 2, and then add it to the second row, right? And in that case, we will make this value as 0, 0, and 0, right? And then this guy will not be 0, right? So in this process, we try to create this value as 0, but somehow the other values became also zeros, but not the last one. The last one is not becoming 0 because their ratio is different at the last constant value. So in this case, they will create 0 equals some non-zero. Minus 2, it should be minus 2, right? So if we just multiply them by minus 2 and then add it to the second row, it will create the equation of 0 equals minus 2, right? So again, we see all zeros because they are they are parallel, which means they have the same ratios between the corresponding coefficients, but not the constant values. So they don't have the same ratio, and that's why we see non-zero at this right hand side. Okay, so this exact case, I mean, this is the only case when we have when we have no solutions. Okay, given our linear systems, it doesn't matter whether we have 2 variables or 3 variables or 4 variables. Yeah, this is the only case when we have no solution. So again, let's try to generalize our findings. Okay, so we try to do all these different row operations to create this staircase, but suddenly at some point we created all zeros except for the last value. In that case, yeah, there is no solution, right? And also, this is the only case where we have no solution. Okay, so all zeros except for the last non-zero value, then that is the same as no solution case. Okay. Questions so far? Okay, now let's move on to the chapter 1.2, and then this is a virtually, I mean, there is no new contents in this chapter, but we now learn the new terms that about what we already learned in the previous chapter. So the title contains this some weird word called echelon. It's echelon, not echelon or something. Okay, it's echelon. Yeah, I think it's in French or something. Okay, so it's pronunciated as an echelon form. Okay, so the staircase kind of shape of our matrix is called echelon form. Okay, so that is actually echelon form. I mean, the definition itself of this echelon form is that staircase of a matrix. Okay, but now we learn how we can formally define the requirements or conditions of these echelon form. I mean, how can we verbally and correctly say the requirement that we have satisfied for this staircase shape? Okay, we now have an intuitive understanding about what the staircase should be, right? But let's try to verbalize or verbally state the requirement for satisfying this staircase shape. In order to do that, let's first define this leading entry. So it's in bold case, so you have to pay attention to this term. It's quite an important term. Okay, leading entry. Leading entry. Leading entry is simply the first non-zero value. Again, it's the first non-zero value, but it could be in terms of its row or if it in terms of a column, right? So we have a horizontal or vertical axis, right? Because we have a staircase of moving down or to the right, right? But this leading entry is defined per row, okay? So yeah, I'm gonna give you, or I'm gonna ask you, what is the leading entry in the second row? Okay. Again, the leading entry is defined in the row. Okay. And then I'll give you the second row and then ask what is the leading entry of this second row, and that is what? This one, because we just scan from the left to the right and then find out what is the first non-zero value. Okay, that is the definition of a leading entry. And then it's actually quite related, and the reason for defining this leading entry is because this is actually, yeah, in the case of a staircase, this is actually the first value or the first wall when we go to the right. Okay, so this is acting or playing a role as of a wall. Okay, when we go to the right. Okay, right. So if we draw this staircase and then we move to the right, and this is the first wall that we meet. Right. So that is corresponding to this leading entry. Okay, so now it's time to verbally formalize or define this staircase shape of our matrix, which is called echelon form. The first condition is all all non-zero rows are above any rows of all zeros. Okay, so it means, yeah, so we saw some unfortunate or really sad case of this, right? Where we have all zeros except for the last one. I'm not sure if it's a sad case or a happy case, because once we find this, and then we are free to go, right? So we can just, yeah, we are done with solving this, this problem and move on to other problems, or, yeah. But anyways, but what if we have exactly the same ratio of the value? So for example, in this case, what should this value be? So it was all like 2 times of the original value, and then if we see 12 here in this case, then this is the case where the 2 lines or 2 hyperplanes are coinciding each other, right? So there, in that case, we have infinitely many solutions, right? But when we have like a third or kind of more equations, and then it means these 2 hyperplanes are the same, but we still have to satisfy some other equations, right? In that case, we have to consider the intersection between all the different planes, or all the given equations, right? So, but still, if in this case, what will be the corresponding row when doing the row replacement on the second row or the second equation? It will be, sorry for a bit messy slide, but it should now be 0, 0, 0, and also 0, right? So sometimes we can meet, or it can happen that this kind of all 0 rows are showing up, right? So in that case, it's called the 0 row, of course, right? 0 row is just rows of all zeros, right? Okay, so the first one is about these 0 rows. Okay, any rows of all zeros. So those kind of equations of all zeros should be below. Should be below the all the non-zero rows. Okay. So this case, let's think about the case where we violate the first condition. In that case, let's just use 0, some non-zero as x. Okay, x means non-zero. Yeah, then 0, 0, 0, x. Right. So up to this point, if this is our matrix, then this is clearly satisfying our staircase, or this, we can call that as an echelon form. But what if we have this? Yeah, what if we have the second row of all zeros? In that case, let's try to draw the staircase using different color. Okay, so we stepped up or down, and then we go to the right, and then we we suddenly end it, right? So we we went to the far end at the right, okay. But now let's assume that we go up or down, and then now in order to have for this value we have to go to left, right? So it clearly violates this staircase, right? So as it is, staircase shape is like this, so something like this. So this is not clearly our staircase, right? So this is clearly violating our condition. So all 0 rows should we put them into the bottom part. I mean, we put all 0 rows into the bottom part. And how we can do it is we are okay to just simply switch between them, right? Because it's equivalent. I mean, it's just nothing but changing the order of two equations. Okay, so the first condition is like that, but if we see all 0 rows, we can simply move them to the far, I mean in the bottom part. Okay, but at least this is one condition that we have to check whether our matrix is has a stair form or echelon form. Now let's move on to the second one. So we now consider this a leading entry of a particular row. Okay, and then we now consider the corresponding column, and then we look at the bottom of that leading entry, and then we should see all zeros to the bottom of that leading entry. So again, let's see. Yeah, so is this a staircase shape or not? Or is this echelon form? It's not, right? Because we have to go up twice, right? Which is not allowed, or it's not possible, right? And that means when thinking about the second row, what is the leading entry? It's this guy, 1, right? And then we look at the bottom of this entry. So although we obtained this leading entry from this row, but once we found that leading entry, then we now look at its column or this vertical line. Okay, but we look at the bottom part and then see if there are any non-zero values below of that leading entry. And if we see any non-zero values below that leading entry, and then it's no longer a staircase, or it's no longer echelon form. Okay. And so, in other words, we have to see this value as 0. Okay. So that's another condition that we have to satisfy in order to see this staircase shape or echelon form. Okay. Okay. So. One thing to note is that we now consider some conditions in order that we have to check whether a particular matrix has is a staircase shape or not, right? But even if a particular matrix is not yet a staircase, but we don't need to be frustrated. We can still make them into staircase matrix. Okay, so. So it's always true that we can always make one matrix which is not yet staircase into staircase matrix. Okay, so we can always do that. And how? We do 3 different row operations that we learned, right? So in this case, what we did was to do the row replacement by changing the third column so that this value become 0, right? Okay, then the third condition about this echelon form is all entries in a column let's see. Each leading entry of a row is in a column. So the condition that I just described is actually corresponding to the third one, right? Yeah, sorry about that. But what is the second one? Each leading entry of a row is in a column to the right of the leading entry of the row above it. Yeah. So it's quite complicated, right? So honestly, I cannot understand this as it is. But let me just explain it intuitively. Okay. So this is about, let's see. So this is one nice staircase, right? And then now let's consider the leading entry of each row. Okay. So let's think about the first row. And then what is the leading entry? 2.
2 on the left side.
Yeah. Okay. What about the second one? The leading entry is this one and this one, right? And then let's think about the corresponding column of each leading entry. And then this guy is belonging to the first column, and this guy is belonging to the second column, and this guy is belonging to fourth column, right? Because it's belonging to the fourth column, right? And then the second condition in this echelon form is saying that the leading entry of the above column, the column of that leading entry should be to the left of the leading entry, the column of leading entry in the below column. So it means this one was extracted from the first row, right? And then that is having the column index of 1. And then this one has the second, but it was extracted from the second row, right? And then it's first row, right? And what it means is this number is larger, and then the corresponding column index should be also become larger. Okay, so this relationship cannot be reversed. And that means, I mean, if that is reversed, then the column of the first row, I mean, that first, the column of that leading entry is located on the right side of this. So leading entry is somewhere here, and then it's corresponding to that exact violating case, because in the first row, it was belonging to the third column, and this guy was belonging to the second column. So in that case, the staircase is broken. Okay. Okay, so that is this second condition. Okay, so that's it for today. And let's meet next Tuesday.
책을 5판으로 산 거고 아니에요?
5판이요.
5판을 PDF로 바꾸면 하는데 저거 내용하고 약간 매치가 안 돼가지고.
어디가 매치가 안 돼요?
그러니까 여기서
네.
그게가 5판이라고 해서 5판을 정확히 5판으로 보여놨는데 저게 어느 몇 페이지 걸 얘기하는 건지 캐치를 못해요. 내용 자체는 이해가 되는데.
네. 아, 그 책에 그 에슐런 폼 1.2에 있을 거예요. 네. 그래서 1, 2, 3번까지 우리가 한 거고요. 나머지 두 가지의 조건이 있어요. 그거를 이제 다음 시간에 설명을 해줄 거고요.
저 마지막 게 이해가 안 돼.
네. 이거요? 아,
그냥 다 밑에 리딩 포인트 밑에 제로가 있어요. 그냥.
네, 그러니까 보면 어떤 로우에 리딩 엔트리가 있어요. 그 리딩 엔트리가 속한 컬러가 그러니까 first row에서 내 리딩 엔트리 몰랐어요. 근데 그 첫 번째 로우에서 리딩 엔트리 몰랐어요. 그거가 어떤 컬럼에 속해 있는데 컬럼은 이 로우에 위에 있는 로우, 그러니까 이제 첫 번째 컬럼을 고르면 이게 조금 이상이고, 예를 들면 세컨드 컬럼에서 세컨드 로우에서 리딩 엔트리 골랐어요. 제가 속한 컬럼은 이 로우 위에 있는 로우들의
세컨드 로 위에 있는
세컨드 로우 위에 있는 로우들의 뭐의 오른쪽에 있어요? 네, 뭐의
자 이거
오른쪽에 있어야 되냐 하면 리딩 엔트리인데 위에 있는 로우들의 리딩 엔트리.
어쨌든 제가 이해는 못했지만 그 에셔런 폼을 설명하는 건
네, 맞아요. 그러니까 이게 스테어케이스라는 거는 이렇게 아래로 내려가면 역시 오른쪽으로 가야 돼요. 그 말은 이 저기 벽의 위치가 점점 더 오른쪽으로 가야 된다는 거예요. 내가 내려가면서.
그 얘기를 하는 거예요. 그 스테어 베이스랑 에셔런 폼이 똑같은
네,
경우.
정확하게 똑같이.
그럼 에셔런 폼이 다 레이딩 포인트가 1인 걸 의미해서 1이 아니잖아.
1이 아니어도 상관없어요. 그러니까 벽이라는 거는 이제 난제로면 벽으로 인정하니까 1은 아니어도 돼요. 근데 걔네들이 다 1이어야 된다라고 하면 그걸 이제 뭐라고 그러냐면
다른 용어.
네, 거기 리듀스드라는 말 하나도 없죠. 리듀스드 에셔런 폼이라고 그래요. 그 다음에 또 하나 조건이 또 있는데 그건 뭐 다음 시간에 할 텐데 리딩 엔트리를 우리가 1로 만들어요. 그냥 스케일링 하면 돼요. 그죠?
리딩에서 1을 만들고 나머지 다 0으로 만들고.
네, 그 아래쪽이 0이어야 된다는 조건이 있었고요. 근데 이번에 위쪽도 다 0이도록 만들어야지. 이게
그러니까 이 대칭선을 제외한 나머지 다 0으로 만들고.
네, 그러니까 리딩 엔트리를 따졌을 때 그게 이렇게 그러니까 저기 로우가 밑으로 내려가면 얘네들은 오른쪽으로 가야 되고요. 그 다음에 얘네들 하나하나 리딩 엔트리 아래쪽을 보면 얘네들이 다 0이어야지 이게 기본적으로 에셔런 폼이고요. 이 위쪽도 다 0이고 이 리딩 엔트리의 값 자체가 1이 된다? 그러면 그게 이제 리듀스드 에셔런 폼이라고 해요. 그러니까 아래뿐만 아니라 위도 1인 거. 아니, 위도 0인 걸로 만드는데. 이거 위쪽을 0으로 만든다는 거는 이제 뭘 의미하냐면 아까처럼 x3를 이 위쪽에다 대입하는 거 있죠. 그래서 x3 이퀄 뭐였지 3이었나?
그런 쉬운 폼으로 변환하기 쉬운.
네, 에셔런 폼으로 이렇게 만든 다음에 또 위쪽으로도 또 다 대입을 우리가 했잖아요. 거꾸로 올라가면서 거슬러 올라가면서 그게 이제 위쪽을 0으로 만든다는 뜻이에요. 네? 뭐 있어요?
화요일날 보고
아 그래요?